Okay, good morning. In the program, there's actually two presentations from the Delphi team, both the Delphi C3 and the successor satellite. We have changed things a little bit, sorry Jim, but we'll be on time. We're going to give 4 presentations. I will start off with an update on the satellite. Where are we now? I mean, the satellite's flying, but I'll give you all the inside details. Then afterwards, Wouter Weggelaar, PA3 Whiskey Echo Golf, will continue with the local oscillator design for the radios on board Delphi. Then Geert Brouwer will have a presentation about the antenna system for Delphi, the antenna boxes and the tape measure antenna system, as you can see it on the model over here. And finally, Martijn de Miliano is going to tell you all about the next project, Delphi Next from Delft University of Technology, which is another satellite from Delft. So first of all, an overall update of Delphi. I think most of you are familiar with Delphi. For those who are not, I'll just give a very short update on the satellite. It's actually the 4th Dutch satellite. There have only been 4 satellites from the Netherlands at this moment. And it's the first Dutch university satellite. The project was actually started in November 2004. And the satellite was launched on the 28th of April this year, successfully. It's based on a 3-unit CubeSat. There's a full-scale mock-up over here. So this is the actual size of the satellite. And one of the interesting things is that it doesn't incorporate a battery. So there's no battery inside the satellite. So it's fully solar powered. And we had a couple of reasons for doing that. The most important ones were that we're testing a solar cell experiment, the thin film solar cell, and an autonomous wireless sun sensor experiment for basically it's about testing a sun sensor which has no electrical connection, just an RF wireless connection to the onboard computer, and it's powered by its own solar cell. So the satellite actually does only need to be active when in sunlight, and it does not need to be active when in eclipse. Furthermore, batteries, well, they dictate quite strict temperature ranges, and they may make the design quite complicated. So that's why we opted for not using a battery. In the end, it turned out that not doing that made the design complicated as well, because the complexity was shifted towards the software design. The software, the proper sequencing, switching on and off of all the subsystems became very important. So it's actually no free lunch. The satellite does not have any active attitude control. It's basically just tumbling. However, it does incorporate a magnetic, passive magnetic attitude control system, which stabilizes and lessens the rotation rate over time by using hysteresis materials. It's got a 1200 baud BPSK VHF downlink, which has been on for over the last 3 months on 145.930 megahertz. We've had an abundance of telemetry frames from amateurs worldwide, so I can already say thank you very much. We'll talk about that later as well. And as of yesterday, we switched on the linear transponder, the mode UV transponder. We have had 3 months of science mission. We have had 3 months where we have collected all the science data about the experiments, the thin film solar cells and the sun sensor. And yesterday we turned on the transponder. Actually, we had tested the transponder discreetly before, so we knew that it worked. But yesterday we opened it for free use. And some of you were there. We were trying to make a QSO over the transponder as well, using 2 FT817s. We weren't able to do so, probably because of all the other people also trying to make QSOs, because we heard other people on the transponder. We heard an SP5 station in SSB, an SP9, I think it was SP9 FPP in CW. So the transponder is working, and actually the first QSOs have been made. Although we haven't seen a mention on the BB yet, but we are confident that the first QSOs have been made.
There was confirmation from New Zealand last night that it was still on, but I'm not sure about QSOs.
Confirmation from New Zealand that the transponder was still on?
Yeah, still.
Oh, that's good. So it was on just before entering eclipse, so that's very good news. We have a very active amateur in New Zealand, Alan Cresswell, ZL2BX, and he is still listening and submitting telemetry frames and listening almost every pass, so that's great. So that just shows you the tremendous help that we've gotten from the amateur radio community. I'll talk about the actual linear transponder operations later in my presentation. So, where did we leave last year? Well, we were actually integrating the satellite to the actual flight model. And what you see here is a picture of us in India, in the clean room in India. Well, cleanish room, I should say. It wasn't all that clean. At times, people were just walking in without clean room clothing, vacuum cleaning the clean room, but it was sort of clean, so that was good. And so here we are assembling the satellite, assembling the solar panels, doing the final checks, and testing whether everything is okay. And you can see our special mascot on the table, if you look closely, a Dutch windmill. More about that tonight during the auction. The satellite was launched on a PSLV in the NLS-4 launch system, which was brokered by the University of Toronto. And Delphi is actually in the pod to the left, in the X-pod. And here you can see the configuration with the primary payload, Cartosat, an auxiliary payload from India, and the other auxiliary payloads, the CubeSats. And in the real world, this looked like this. Here you can see all the pods. I think this is Qt 1.7. These are the other pods, and this is the pod for Delphi. And if you look at the picture over here, you can actually make out the sticker on the end of the pod, the Delphi sticker, which we managed to put on, and we just put on some Kapton tape. And the Indians were okay with that. There was no problem. And to the side, there's another Canadian satellite, which was actually added at the very last moment to that launch. It's a microsatellite. Well, it was a very interesting time in India. We were there for about 10 days, doing all the final integration and all the checks. And of course, they wanted us to show around the base as well, the launch base. That was interesting because actually we were witnessing the rollout of the fourth stage of the PLSV rocket. This is the truck that carried the fourth stage. You can see it actually covered under the blanket behind on the truck. And it was a big ceremony with lemons, which they put in front of the wheels of the truck before it rolled out of the building. And a couple of coconuts that were smashed on the ground, and then they sprayed the coconut milk on the lorry to basically make a good offer to the gods. And fortunately, well, that went okay because the launch went perfectly fine. This was the actual launch vehicle. On the left, it's the C9 PSLV in the vehicle assembly building, so just before launch, just before rollout. And this is the launch vehicle on the. And with the India, we have been to the vehicle assembly building, and it's been really impressive to see the PSLV rocket standing there, knowing that our satellite is somewhere up there. That was really, really rewarding. So finally, well, you probably know it's taken a lot of time before the satellite actually got launched, because actually the launch was planned on the 30th of June, but there were a lot of delays due to the schedule, due to weather, and due to supplies for building the launch vehicle. Finally, the 28th of April, launch day was there. And at 05:53, actually that is Dutch time, so it was 03:53 UTC. It was launched, and the launch went superb. It was all okay. And it took a lot of time before we actually had confirmation of deployment of all the CubeSats, because the launch vehicle had gone out of range of the downrange tracking station. So it took, well, I think it must have taken half an hour, but it looked like ages before we had positive deployment confirmation that the CubeSats and Delphi was out of the pod and out of the launch vehicle. So then it was just waiting for the first report for the satellite to be heard, and we knew that it would come out of Eclipse at around 7 o'clock Dutch time over the US, and it would start to deploy autonomously. So it would start to deploy the antennas, it would start to deploy the solar panels and start transmitting. Nothing was heard actually until the next pass over the US, when Rick Mann, a radio amateur, not sure about his call sign, he received Delphi, and he made a recording of that using his MacBook, his PC, and an IC PCR 1500 receiver or something, and an arrow antenna actually. He was with an arrow out on a hill. He sent the recording to us, but the recording was so noisy that we actually had to listen to it for 3 times before we could actually positively confirm that it was Delphi. But it sounded like Delphi in science mode. We've been hearing that sound for weeks on end when working in the clean room, so we knew what our baby would sound like. So that was a great moment. We were all very happy, and very happy that Delphi was working. We knew that there would be passes over Delft shortly after that. But then, during those passes over Delft, there were actually 3 passes over Delft. We did not hear anything. So in the first pass, we were just listening, using the supplied 2-line elements that we got from the launch service provider, from the PSLV. But we did not hear anything, so we got a bit frightened. And I mean, we're thinking all sorts of crazy things. We were actually thinking that this guy, this Rickman, had actually faked the wave file. But I phoned him up, and it sounded sincere, so it must have been okay. But nevertheless, we were thinking, well, maybe it has worked for a very short time, but it's not working anymore. And we could hear the other CubeSats. Of course, the Japanese CubeSats, well, they always work. We could hear them on 70 cents. They were booming in, basically, but no sign of Delphi. So we started contemplating, started thinking, well, what happened? We actually, the next pass, we already started to transmit commands to the satellite. We actually prepared reset commands, so we prepared for the worst. And only at 5 minutes to 2, we received a signal. And what we did is we pointed the antenna into a fixed direction because apparently, as turned out later, the TLEs were wrong. They were 10 minutes ahead, the TLEs that we had gotten from the launch provider. So, and that was, well, 10 minutes, and well, you know, that was really a lot of time. So finally, we were listening. Actually, the video of that is on YouTube and on our photo blog. I think most of you have already seen it. You can see us sitting in the ground station and finally hearing a very faint signal emerging out of the noise, finally, and also decoding telemetry on the computer screen. And that first telemetry was great because everything was nominal. Everything had deployed. All the solar panels had deployed, the 4 solar panels, and the 8 antennas had also deployed. The backup radio was working. We did not know why, because it was on the backup downlink, because it was supposed to start transmitting on 145.870, but it started transmitting on 930, which is the other radio. Delphi has 2 radios. In the end, that turned out to happen during initial deployment, and we had built in a mechanism that would try the first radio for 5 times, and if it didn't respond, it would go to the secondary radio. And apparently that is what happened. So that mechanism had worked. So it was on the backup downlink. And that's probably also why quite some people have not heard it, because they were listening on the primary downlink on 145.870. Well, today we can say it's 100% mission success. The science mission has been accomplished. We've got loads of science data of all the experiments. And we were very proud to have Delphi receiving an Oscar number, Dutch Oscar, Delphi Oscar 64. On May 15th. That was a great honor for us, for the entire team. So thank you, Amsat. A bit more about the radio amateur network. We were overwhelmed with the response. We knew that there would be quite some people listening, but we had never expected that there would be so many people listening and also contributing reports about signal strength, rotation rate, fading, things like that. That was great. At this moment, we have 281 amateurs who have actually registered for an account for the Rascal telemetry decoding software. And there's quite a bit more which have not registered, but which are submitting telemetry using the guest account, which is also seen by almost 3,000 downloads of the Rascal telemetry decoding program. So there's 3,000 copies around somewhere. One of the top telemetry submitters is, well, the first one is JA0CAW. He is very keen on listening to Delphi. Every time we can see in the Orbitron screen that Delphi exits Eclipse over Japan, the minute later we get telemetry from Japan, from this guy. That's great. PA0DLO second, and ZL2BX, Alan Creswell is third. Not sure about the actual amount of frames that they decoded, but a lot. Around 20,000 JA0CAW, so that's amazing. This is the actual rate per day, the actual number of telemetry frames submitted. There's some nice variation to be seen. Actually, well, you can see that the activity was really large in the beginning. But still, at this time, at about 30 days after the mission start, we still have, sometimes we have days like we have 3,000 frames a day, 3,000 or 4,000 frames a day. So that is still really a great amount and still very good information to, for us for analyzing the behavior of the satellite. This is a printout of, it's not even all the amateurs because it's on another page on the Google Maps, but this is the amateurs in the network that we have. And actually, this shows also the potential for an amateur network, and I think also the great potential for a network like Genzo. You can see the very nice distribution of amateurs. People in New Zealand, Australia, Argentina, it's basically all over the world, so it gives great coverage. This you're probably familiar with, the Rascal program. Basically, the program, well, it decodes all the telemetry. All the housekeeping and payload telemetry can be seen in this screen. This actually is a rare shot of Rascal because this shows telemetry from the primary radio, which is on 145.870.
I think this was during a test because I see undeployed stuff on the right. So.
And this is, oh right, this is during a test, you're right, because this is undeployed. This is, okay, this was in the clean room probably, you're right. That's why, okay. Because, well, you've probably seen in real Delphi everything is deployed fortunately, so that's good. And the program has functioned like a charm. We've only had, I think, we have a version 1.01 right now. There's some minor issues, but other than that, it's working fine. And it's still available for download. This is the first IV curve of the thin film solar cell experiment, the payload that we have on board. This was actually already made on launch day, so this was actually just on the first day of the mission. And here you can quite nicely see that one of the thin film solar cell panels is illuminated and producing a very nice IV curve, and another one is illuminated just a slight bit and produces just a bit of power. And in our telemetry database, we have, well, a tremendous amount of frames, and since we have so much, we have not even been able to fully analyze the entire database and the entire amount of telemetry. That's still a lot of work. Actually, thesis assignments for students are being written right now for analyzing telemetry because there's so much very nice valuable data in the telemetry. Well, this is just an intermezzo, just eye candy, basically, of the satellite. Showing you the satellite just before integration. Actually, well, this was the flight model. The model that we have over here is it's a mock-up, but some of the boards are flight standard. Some of the boards are mock-ups, but some of the boards are flight standard. For instance, the radios that do transceivers are flight standard. Something about the satellite behavior itself. It took us about a week to characterize the actual behavior of the satellite itself. What we have noticed is that, and you've probably noticed that as well, is that sometimes the downlink switches off erratically or abruptly, basically. And first we were thinking that that might have to do with power, with certain attitudes that we didn't have enough power, and the radio is switching off at that stage. Further analysis and testing has led us to believe that that is not the case and that it's a databus issue. And actually that issue had been known shortly before launch, but we did not have any time to correct it anymore. So we left it as it was. It's not a critical issue. We can transmit a single command to the satellite and recover the satellite again. And that's how we do the daily operations right now. When it's over the ground station in Delft and it's not on, we transmit a command, and usually at the first command it's received, acknowledged, and the satellite comes on back again on the downlink. Rotation rate, question mark. We have seen the rotation rate decreasing from about 10 degrees a second, which was relatively large, well, to almost zero. But we're just starting to analyze the telemetry, the housekeeping telemetry, for actually analyzing and getting high fidelity data on the rotation rate. So, well, we just don't have any numbers yet on rotation rate. We know, however, from observations from the polarization of the radio signal that the rotation has decreased quite a lot. And here also observations from amateurs have helped a lot. For instance, BA3GUO, Henk, he has made a lot of recordings and a lot of graphs of the signal strength over time. And that was really helpful in assessing the coarse order of magnitude of the rotation rate. Another observation that we saw on the BB is that sometimes the transmitter sounds distorted and it does not decode anymore in Rascal. And that seems to coincide with a low bus voltage. Nominally the bus voltage inside the satellite is 12 volts, but it tends to drop sometimes to about 7 volts, and that's in the cases where only one solar panel is illuminated and supplying all the power. And as soon as the satellite rotates a bit more, the other panels get illuminated and the bus voltage comes up again. And what happens is that the power amplifier, the PA stages and the driver, they start to distort, and they start to clip. That's basically why you hear the distortion. But again, that's not a critical issue, and that's solved when the satellite rotates just a bit more. The internal temperatures are just fine, within limits. Those of you who have been observing the telemetry in Rascal have seen that telemetry is generally at about a balmy 15 to 20 degrees C. So that's perfectly within margin. We have seen temperatures from about, let's say, 0 to about plus 38 degrees at the end of the orbit, just before the satellite enters eclipse. So that's perfectly within our predicted values. One of the other things that we have observed is that the command uplink receivers have drifted a bit in frequency. And I think that the AAU Set2 satellite have also experienced frequency drift. We have seen that on the uplink, frequency have drifted a couple of kilohertz. We're using crystal oscillators. Wouter Wegla will tell you all about that after my presentation. And we've seen some aging of the crystals and the frequency drifting up slightly, but it's only about 2 to 3 kilohertz, so that is okay. And we actually measure the Doppler voltage of the command receiver inside the satellite, and we transmit that down into the telemetry, so we can see the actual frequency offset on the uplink. So we regularly command and check whether the frequency is still okay, whether we're still in the center of the command receiver, and so we should be able to counter that effect. We had a lot of fun, and we're still having a lot of fun. It's great to be listening to the satellite that you've been building with a team and staring at the blue sky with an aero antenna and just receiving a strong signal of 2 meters. That's, well, priceless. It was amazing. So we've been doing this quite often, actually. So our daily mission operations are basically, commanding the satellite when it's off. So we are commanding it back on using recovery commands, as we call them. And we can do it remotely. We can remotely log into the ground station. That's actually also how we switched Delphi into transponder mode yesterday, by just remotely via VNC logging into the ground station. And we use a linear amplifier on the uplink. We use about 300 watts right now from a BECO linear amplifier on the command uplink, and that's just to give margin. We know that we can do without, but with this amplifier we can command down to the horizon. And that's also because the uplink receivers are slightly deaf. The noise figure of the receivers is about 6 to 7 dB, so it's not as good as they should be, but it's good enough. As you may have observed about our transponder operations, we were planning to switch the satellite into transponder mode before we went to the Colloquium permanently, but we just didn't have any time. So what we're doing right now is commanding the satellite to transponder mode using what we call volatile commands. So we transmit the command to the satellite, and after the next reset, when the satellite exits the next eclipse, the command is lost and the satellite comes back into default mode, which is the science telemetry mode. So if you don't hear the transponder these days, be sure to listen on 145.930 for the telemetry downlink. And once we get back to Delft next week, we will switch it permanently to transponder mode using a non-volatile command, but that command sequence, it's a bit more complicated, so we don't dare to do that remotely. We prefer to do that when we are present in the ground station. So, a bit more about the transponder itself. It's a linear transponder, comparable to the Amsat transponder, the VO52 transponder, although it's got lower power. Power is about 100 to about 200 milliwatts. It's actually lower than the power which is quoted on the website, 400 milliwatts. And there's a CW beacon at 145.870 and transmitting the Amsat standard high. This is Delphi C3. After that message, there's a commemorative Sputnik message consisting of 6 dits, and it sounds a bit like Sputnik. So if you're listening for the beacon, you might have a listen for that as well. You might hear that signal as well. The uplink is on 70 centimeters, also 30 kilohertz. Well, since the downlink is relatively weak compared to VO52, it's good to have a good receiving station, although we have heard the beacon and transponder on a narrow antenna yesterday as well, so that's perfectly doable. Okay, well, it doesn't stop with Delphi C3. The Delft University will continue to build small satellites, and the last presentation in the Delphi presentations will be done by Martijn, and he will tell you all about Delphi Next, the next satellite from TU Delft. For now, I would like to thank you very much and thank the amateur radio community for helping us so much with gathering so much telemetry data, giving advice, giving technical advice. It's been great to attend all these colloquia, and we plan to attend the colloquium for the coming years as well. So I hope to see you next year. Thank you.